Generic ROS messages work well for basic tasks, but when you start engineering custom robotic hardware, standard data types often fall short. You end up trying to force basic geometric shapes into highly specialized joints. Today, we are building a custom ROS package from scratch. We will define a unique robot status message to broadcast system health and a set goal service to handle request and response commands. Before we begin, ensure your environment is ready. You need a Linux system running a functional ROS installation and an initialized Catkin workspace to manage your packages. Moving from pre-made tutorials to engineering real, proprietary robotic systems requires custom data structures. Mastering this process provides the exact communication formats your hardware demands. Step 1 is setting up the workspace. Navigate to the source directory of your Catkin workspace. Run the catkin create package command to establish your base package, naming it My Robot Messages. Notice the arguments at the end of that command. We are including std messages so we can build upon standard data types like strings and floats, and ROSPy to ensure Python compatibility for our scripts later. Inside your new package, create 2 separate directories. Name one MSG for your custom messages and the other SRV for your custom services. This keeps your definitions organized. In MSG, create robotstatus.msg with a status string and battery level float stacked into one packet. Next, create setGoal.srv. Services handle two-way communication, separated by 3 hyphens. Above are the float inputs, X and Y. Below is the output, a success boolean. Right now, these are just simple text files. They act as blueprints, but they remain completely inactive until the ROS build system compiles them into usable code. To compile those blueprints, we have to update our configuration files, starting with package.xml. Open it and add 2 specific lines, a build dependency for message generation and an execution dependency for message runtime. Next, open cmakelists.txt. The target blocks for add message files, add service files, and generate messages must be uncommented and edited in this sequence. If you omit the message generation component, the build will fail. The compiler relies on it to generate Python interfaces. With the configuration complete, return to the root of your Catkin workspace and run catkin make. You will see the terminal output processing your specific message and service files. Once the build finishes, you must run source dev setup.bash. Skipping this step means your Python scripts won't be able to find the new packages, resulting in a module not found error. Completing this configuration sequence translates your static text definitions into the Python headers and classes that organize your network traffic. You now have custom data types ready to use. Let's put that architecture to work. We'll start by writing a Python script to act as a publisher node. The most important lines in this script are at the top. We import robot status from our new myrobotmessages.message module and setGoal from the SRV module. This proves our Python environment can successfully access the compiled custom headers. Inside the script, we initialize the ROS node and set up our publisher. We then pass our custom string and float variables through the publisher, broadcasting the robot status and battery level across the network at a steady 10 Hz. For the service client script, the logic requires a safeguard. Before sending the X and Y coordinates, the code uses rospy.waitForService. This forces the script to pause and verify the service is actually available on the network before it makes a request. These scripts activate the structural blueprints we built earlier. They take static data definitions and turn them into active, network-aware robotic behaviors. To verify our system, we execute both Python scripts simultaneously. Terminal A on the left runs our continuous publisher node, while Terminal B on the right executes the client request. You can see the system working. The publisher node in Terminal A runs continuously without crashing, and Terminal B outputs a clean goal set successfully message. Our 2 nodes are now communicating seamlessly, exchanging complex variables using a custom protocol built specifically for this hardware. By defining your own messages and services, you move beyond the constraints of generic templates, allowing you to tailor your robot's communication to the exact needs of your hardware.